So our second speaker for the afternoon session is Professor Miguel Tierz from CIMIS, and he will talk about random matrix view of quantum spin and fermionic chains.
Okay, thank you. Thank you very much for the invitation, and to the organizers, Professor Yao, for this wonderful conference. I've been here for the whole 2 weeks and enjoying every day. Also, thanks for the creation of CIMIS, which has allowed me to be already here for 1 year, which I enjoy enormously, and scientifically it's been very good to me and my colleagues. So yeah, let me start by saying that this work is mostly, it's not the recent things I'm doing now, but it's based on this paper with David Perez Garcia, who is a quantum information specialist based in Madrid. Leonardo Santilli, who has been a postdoc at Yao Center for a while. They did a PhD with me in Lisbon, and he will join CIMIS this August already. So this is a work on dynamical quantum phase transitions based on a random matrix approach. And for those of you who have, I see a lot of people here has a background in gauge theory, quantum field theory, etc. Some of this random matrix theory approach that I'm mentioning is very familiar to in gauge theory, because there are some matrix models which originally appeared into the Yang-Mills theory. Okay, before I start for real, let me a bit of advertisement, which yesterday I was saying to some of you that I never do any marketing or advertisement. So the first slide is actually a little bit of just to say that we have this seminar. We have a lot of seminars at CIMIS. I think every CIMIS member has his own seminar. So there are Avogadro's number of seminars per week, basically. So, but nobody wants to give up their own. So mine is this on quantum computation and quantum simulation, strongly correlated systems. So I want to use this as an invitation to everybody attending. Also, if somebody sees this online, YouTube, whatever, consider yourself invited to visit and give a talk. Just need to drop me a line, say, Miguel, when is my seminar happening? And we'll make it happen. So this year I had like around 30 people roughly in these 2 seminars, which is more than I had even for many years in Spain, for example. So I've been enjoying a lot this. And these are the topics that more or less I'm trying to do at CIMIS. And nicely enough, so this is more kind of quantum optics work. Nicely enough, I'm starting to get in touch with experimental groups, because this is all very theoretical work, which I'm trying to do as down to earth as possible. And I'm very excited that here in China there are many nice groups, for example, on cavity optomechanics, etc. And hopefully I can push this to something that is relevant for the real physics and experimental people. But let me quote the Western reference in Groucho Marx, who said, these are my principles, but if you don't like them, I have others. So I'm going to tell you about something a bit different, which I believe is maybe better suited to a number of people here, which is this random matrix approach to spin chains and quantum fermionic systems in 1 dimension. So this is the plan. This is how I plan to organize my talk. There are many slides. There seems there are many slides, but some of this is just 1 slide per line here. So it's not as much as it seems from the introduction. So I will start in the first 2 slides. Basically, I'll tell you what is the main object I'm going to study in spin chains, which is called the Loschmidt-Echo of fidelity. This is just a simple quantum mechanical amplitude. And I will also particularize which type of states and which type of chains I will study. This will be generalized as the talk goes on. But to start with, we'll focus with extremely simple setting, which is the case of XX spin chain, which is equivalent to free fermions in 1 dimension. So it's a non-interacting system of fermions, if you want. And I will be looking at what's called domain wall states, which I will define. It has a very simple definition. The scaling of this Loschmidt-Echo will be important because it's inspired by random matrix theory, namely the planar limiting matrix model that some you possibly already know. And the physical underpinnings of this quantity that I'm studying is related to the notion of quantum quench, where many people works on, and it's a very active field in condensed matter physics, strongly correlated systems. I will just only give 1 slide, and our quantum quench setting is not the most general. And I will also discuss, just give you a slide also, telling you references, and because this has been a problem, that has not been my main problem, but I've been working on and off on this type of thing. Depends on how you count, like for around 10 years, but very on and off, as I say. And because sometimes when I talk about this, people like to have some introduction to random matrices, which is a rather interdisciplinary subject. I will give an introduction on the type of matrix models that I am presenting. And this I can somehow, there are little aspects of this random matrix introduction that I can connect to things that Babak said in his talk, or Tomoki, in particular. For example, I have Andreev identity explicit here. You mentioned it yesterday. But so I can connect a little bit with things that have already appeared in some other talks. But basically what I want to describe is what I mean by a random matrix description of Loschmidt-Echo. Loschmidt-Echo has been studied by many people in condensed matter physics. The random matrix description is a very specific one that is based on this paper, so that it's not a very well-known description, so I like to emphasize it a little bit. And then I will go to the results, which are in this quantum paper with David and Leo, which is mostly because I will be studying Loschmidt-Echo for real-time dynamics, which is experimentally more interesting. Basically, the main result is to show the existence of a phase transition, which, for those of you who are familiar with matrix models, it's related to the famous Gross-Witten phase transition that was found actually in 1980 by David Gross and Edward Witten. But it's a different one, because the matrix model is very close, but not quite, because there is a complexification of what in Gross-Witten model is the coupling constant, because this is necessary to explain, to describe real-time dynamics of the spin chain. And then I will explain what are the differences between standard dynamical quantum phase transitions, because there is a huge literature in condensed matter that by Loschmidt-Echo, studying Loschmidt-Echo as a signature of what is called dynamical phase transitions, because these are phase transitions which are non-equilibrium phase transitions, and it happens, the time variable is not beta, but it's the time. So this is why I call dynamical. And normally it's based on people study dynamical quantum phase transitions by studying zeros of the Loschmidt-Echo amplitude. But there are many differences in this phase transition. To start with, the order is third order phase transition, which is very exotic from a condensed matter point of view, but rather ubiquitous if you know random matrix theory. There are several random matrix ensembles that have phase transitions of third order. And I will try to discuss a little bit what is the experimental accessibility of this phase transition, because these spin chains are well known to be, this is a simplest case of a Heisenberg spin chain, which is well known to have a realization in terms of quantum simulators based on cold atoms. So an open problem would be just to measure with some quantum simulator system experimentally the phase transition. And for this, because a lot of the results are for infinite chains, we have to study the case of finite chains and see how the phase transition persists. If I have time, I will talk a little bit about some open problems that I just realized by kind of talking a little bit again about this subject, which we finished kind of 2 or 3 years ago. And some of these developments, maybe to some people here who are more formal quantum field theory oriented, I believe there are several tools in conformal field theory, etc., which may relate more formal aspects of CFT, for example, with some of these results. But let's see if I have time. If not, I can discuss informally with some of you this. Okay, so let me start for real. And so a proof of dynamical phase transition is the Loschmidt-Echo as a set of fidelity, which is this quantum amplitude here. I will describe it a bit better in the next slide. But basically, is this object here, and this is the amplitude. The Loschmidt-Echo itself, or fidelity, is the probability. So this is the square of this object. So these dynamical quantum phase transitions, that I will give some references, some reviews, because there is a huge literature on this topic. Yes, and here in BIMSA there are some people working on that, or very knowledgeable about the Loschmidt-Echo and dynamical quantum phase transitions. These are signaled by the non-analytic behavior of the dynamical free energy, which is just the log of the Loschmidt-Echo. So we'll focus on this object, for which model we will discuss what is called the XX chain, or isotropic XY Hamiltonian, which can be written as this model here. You can also write these are the lowering and raising spin operators, which are constructed as a superposition of the sigma X and sigma Y Pauli matrices. You can write this, if you write in terms of the standard Pauli matrices, this is sigma X and sigma Y. So 2 copies of sigma X and 2 of sigma Y, 1 in J, J plus 1. So this is the nearest neighbor interaction. We'll study periodic boundary conditions. We will discuss also open boundary conditions within the matrix model changes, but we can study both periodic boundary conditions, which it will be a unitary matrix model, or what we call absorbing boundary conditions that are described by a matrix integration on symplectic group. Okay, so let me be more precise about which specific Loschmidt-Echo. Apart from the Hamiltonian, you need to define what is your initial state that you will make it evolve. So we are going to study a very well-known family of states. We will generalize this a bit later on. It's possible in the formalist to generalize this, but for the physics, the most relevant case is the simplest one, which is when, imagine I have a ground state, which can be all spins up, for example, and then I flip a number of spins and in a consecutive block. So L is the number of spins or qubits if you want, and this is a system of L qubits if you want to see it like that. And then, so I'll flip n of them. So we'll need to remember all the time that L is the size of the spin, which in one of the analyses is taking to infinity from the start. I'll discuss this with more detail. And n will be the size of the matrix model when I'll present it. And it corresponds to the number of spins that I flip in my state, okay? Not the number of total spins in the chain. So this is important to remember. Like I said, this can be generalized. This pattern doesn't need to be flipped in a single block. I can flip n, but in any combination I want, and the random matrix formalism I will present still holds for that case. But a lot of the it becomes harder to compute, but I'll introduce some tools in order how to compute this case of what you can call multiple domain wall. And this is just a single domain wall, right? So you can consider a state of multiple domain walls and still the formalism holds. But for the phase transition, this type of impurity, if you want, the interpretation of having a scattered number of spins flip doesn't change the physics too much because it's subleading. And at the mathematical level, your matrix model has to be generalized to include Schur polynomials. So it becomes quite more technical, but it's doable, and this is one of the things that we worked in the past. Okay, so sorry. No, I don't need to have. There will be no. In principle, no. In general, I don't. I don't need to have the symmetry. I can have n. It's a free parameter for me. Actually, then we'll take a large n. I'll discuss more about the n and L a lot in the yes. Okay, so we define the dynamical free energy in this way, and this type of normalization, which looks very innocently here, but of course, if n goes to infinity, it plays a role. This is inspired by matrix models. So this is the normalization. Because I will present a matrix model description for this object. This is the natural normalization in matrix models that give you the planar limits. So this is why we study the dynamical free energy with this normalization. And this differs from work in the literature where you normalize with a number of qubits. But here we normalize with n squared in particular, because this is the standard matrix model scaling. Yes, and then I will have a rescale time also tau, which is rescaling that. So the critical tau that I will give to you, it will be for tau variable, not t. So again, rescale with n. All these are definitions so far. Why we choose this is because of the matrix model description, which I'll present. Before that, let me give you some references which are not mine. I mean, this is, like I said, a huge literature, both Loschmidt-Echo. So for example, this very long review by Prozen group. And this is a nice review on this. It's already from some years ago. And then for dynamical quantum phase transitions by Marcus Heil is one of the people who has worked the most on this and has several reviews. This is one of them. And like I said, if you look at this review, for example, you will see different type of phase transitions than the one I'm going to introduce. And basically, just to mention here from the point of view of quench a little bit, although this is not the most general setting, that the logarithmic echo, what it measures by its own definition, is the overlap of a state that you make it evolve forward in time with a certain Hamiltonian H0, and then you take the overlap with a state that has evolved with a perturbed Hamiltonian. So, not what I wrote, this is a slightly more general. In your quantum amplitude, you have these two Hamiltonians, but basically this corresponds to the case where, in the case I presented so far, when this H0 is trivial and the perturbed Hamiltonian is the XX model. And like I said, not only will generalize to multiple domain Wallet states, but also nice thing about this description is that I can describe many more spin change models, not only this one. But the phase transition result will be presented only for this model. But the random matrix description of this spin chain logarithmic echo holds for general spin chains and for fermionic chains. So when I fermionize the model, I can also discuss starting with fermionic variables. This will be essentially the last slide, and I think maybe working with a fermion picture is something that can be very, very practical in the future. Okay, so these are a bit the precursors I was mentioning. So like I said, I've been working on and off on this for a while. Also, some are mathematical aspects that I need to. So, for example, this that we published in a math paper, this is needed to describe the domain wall, the multiple domain wall setting I was saying, because then we need a generalization of the random matrix ensembles, which are not that well known in the random matrix literature. So we had in these two papers, for example, we had to develop the mathematical machinery if we want to study this problem in full generality. And by the way, the other day we were talking about degeneracy in Chinese names. In Spain, we also have this feature. So I want to say that these two people are not the same person, because it already happened many times. And apparently there is a third Garcia who does random matrices. And many of my visitors at CIMIS, they always thought it was the third one, which I don't know. So anyway, just a point that we also had a huge degeneracy in surnames. Okay. So different people. The first paper and the last one, okay, this is the same, and we added the magic of Leonardo to but the first and the last, the same people, yes. So, please, Leo.
This whole weight phase transition.
Yes.
Free energy at zero.
Right. Yeah. Yeah, exactly. Yes. But yeah, I'm going to say, I mentioned it because in the appendix, in the supplementary material of this paper, which maybe is not the cleverest thing to do, is where we presented the fermionic picture. That would be the last slide, but I won't say it. So the reason why this paper is, well, these ideas have been used to this Hawking page, but it's a bit different problem because we randomize the spin chain and then we have to take an extra average over the interactions between spins. So the setting here is differently. But the reason why I added to the list, not only because it's the most recent, but also because in the appendix, we developed the fermionic picture that applies to, so all these deal with the spin variable description of the Hamiltonian, and here we do it with fermions. And I believe this fermion description has can be more useful for their, so I won't say anything about, but the set of ideas start the same, but this is a randomized spin chain. Physically, the setting is different. So, yeah, basically the first one that started, the bad thing of preparing the talk is I realized that 10 years have already passed, but this is I'm going to present, but for the case of imaginary time dynamics. So this corresponds exactly to the same Gross-Witten matrix model, although we discuss it in the context, there's been the previous talk deal with effective field theory. In low energy QCD, when you put the problem in a box, there is the Lloyd-Willer-Smilga integral that formally, mathematically, the matrix model is the same as Gross-Witten. So we did that, but this is way easier to analyze mathematically because simply we did imaginary time dynamics. Then the only parameter in the matrix model, it's a coupling constant, which is real, and it's easier to analyze. The difficult part here, so this paper is way more technical than this one, for example, is the fact that the coupling constant now is complexified, and this makes it much harder. Okay, I will explain this in full detail. Okay, but let me give you a quick explanation of the mathematical underpinning of my description of the Loschmidt echo, which is based on unitary matrices. These are unitary matrices, and I'll talk about this. But not only I want to talk about unitary matrix, which means integration. These are Lie group integration, and so these are integrations over, for example, UN group. But I like the fact, and it's very relevant, and for statistical mechanics-oriented people, they are more familiar with the fact that this matrix model are actually determinants, and they're actually determinants of Teplitz matrices. Teplitz matrices are matrices which are the determinant of matrices which are constant along diagonals, the elements, and normally they appear a lot, as you know, in physics when you have translation invariance. This is why you have all this strong symmetry. And because we are discussing the model with periodic boundary condition, that's the case here. So my point would be this is a very old identity. So random matrix theory has many origins, depends on which field you come from. Interestingly enough, this is just simply what is called the Weil integration formula, which tells you that if you integrate a class function on a Lie group, you only need to integrate over the maximal torus. So basically, you need this is U1 to the n. So this is why in your talk, I mean, I was still okay that it could be a unitary, because if you integrate over, so these are phases. So this is the Lie group. This is the Lie group. Yeah, well, if it's a square, it's not necessary, but yeah. And the other difference, because you were discussing then the extension to beta ensembles, this is very important. And I do this explanation because normally in random matrix theory, both are known now, but people normally, the Hermitian comes first, right? The people discuss models on the real line. But maybe eventually, as you had, the integration contour can be not on the real line. But they are Hermitian matrices, they have this form here, but then these are not phases, are real variables. But then for symplectic and ortho, you have beta 4 and beta 1, as you said. And then you can extend that to beta ensembles. Here is different because if I change the group, it's not the unitary group, like I'm doing here, and if it's symplectic orthogonal, you need to. This is basically the hard measure for the Lie group. So this is not beta 1 or beta 4. So if you, I'll show it explicitly. So that's another difference. And the fact that the integration is compact has a lot of implications. And this determinantal description also holds for Hermitian matrices, but then you cannot consider Teplitz. These are Hankel matrices, which are a bit harder to analyze in a sense. Okay, so this is well known, and like I said, for example, you can see this is a Lie group textbook by Daniel Bump, a mathematician in Stanford, who has a chapter on this. So basically, the origins of random matrices, normally the people now doing quantum chaos, everybody cites the pioneering works of Wigner, Dyson, etc. But really, the underlying mathematical structure was way before. For example, for unitary. So one way you can learn about the unitary random matrices is by studying. Well, this is the only textbook I know that has this approach. But this is a result by Weil. So you already see random matrix theory there. Yes. Well, because this is also a mathematical conference. So the origins of random matrix theory go actually to Hurwitz, etc. So, but anyway, this is very well known. Like I said, this identity is more than 100 years old. But this can be generalized to the case of not Teplitz matrices, but Teplitz minors. So minor is just like we studied all in linear algebra in the undergraduate, is when you compute the determinant after striking a number of rows and columns, and you normally compute minors to compute the inverse of a matrix, right? So imagine you have a Teplitz matrix, and then you strike in a certain pattern both rows and columns. Of course, and then you can write the Teplitz minor in the most general way like this, because you need two partitions that encode the striking of the rows and the columns. Notice one thing, that a Teplitz minor is not longer necessarily Teplitz, because only very simple patterns of striking will preserve this property of constant along diagonals, right? This, for example, this one doesn't. If I had done a corner, then I would, of course. So these are no longer Teplitz matrices, which in principle is a very crucial, but still nicely enough, they satisfy this identity I showed you before, which is also goes by the name of Heinz-Sego, but there are different names associated to this. The price you need to pay to generalize this Teplitz minor, is the fact that you need you have two insertions of sure polynomials in your matrix model. And if you approach this matrix model, you had approached them before from physics. This structure is the biggest generalization I know of this Teplitz determinant matrix model equivalence. So I don't know of anything more general in this sense. But if you come from physics, you have encountered most likely this type of, because for example, when you do localization in supersymmetric gauge theory, if you compute a Wilson loop instead of a partition function, normally you need to add a trace, which in the most general representation, it will be a sure polynomial. So in localization, for example, in Chern-Simons theory, it has a localization property, Chern-Simons on S3. If instead of the partition function you study a Wilson loop, you will have this. Normally, you don't see it in many papers because people only study fundamental representation or symmetric, antisymmetric, and then this has the form of a simpler trace. But most generalized this. And this two case, for example, in Chern-Simons, this appears if you want to describe a Hopf link. After localization, you will have something like that. So from gauge theory, I was familiar with this, but also in this spin chain problem, if in my ket, in my logarithmic echo, I flip the spins in a certain pattern, I need one of these, and in the bra, I do the same in another pattern, I also need this. So for the spin chain problem, this is the most general description of the logarithmic echo amplitude if my domain wall state has multiple domain walls. But people in statistical mechanics, maybe that's so far at least, is a bit overkill, and there is not much work on this multiple domain wall states. But if you are interested in that, you can do it. You have to do this. If you are familiar with the random matrix literature, there is no standard, whereas there is a standard way of how to compute this guy, for example, with orthogonal polynomials or with Sego theorem, etc. There is no textbook approach when you have insertions of sure polynomials. So you are a bit on your own, so you have to know how to handle this. And in some of these papers, we did larger methods to describe this. And this is some identity that Tomoki mentioned yesterday in his talk, because his models these IBGM models are more complicated. They are more involved. Sometimes a two-matrix model, but they have this determinantal structure also. So, which is what makes these kind of things that solvable in a sense. So this is a very old identity from the late 19th century, but extremely powerful. If you want to learn something about random matrix theory, if you learn this identity, you learn a lot from in random matrix, because it's extremely useful. In particular, is the one that allows this identity shown before, or this generalization here. If you come a bit from combinatorics, you can see this as the continuum version of the Cauchy-Binet identity. And Cauchy-Binet is basically this with summations. So basically, it tells you that the integration over this type of measure, but with a determinantal structure here, is equal to whose entries are integrals of the functions that. What is sigma? Sigma is your weight. For example, in the case of a Gaussian ensemble, is a Gaussian factor. So the sigma actually will define. So this basically, you have this, depending on which symmetry you have, you will have a certain type of Vandermonde. So if it's Hermitian, you'll have these two determinants. Basically, is the determinant square that we've seen before, and it's very well known. And this is what defines the model, the weight function. So, yeah. So one consequence of this, by the general with sures, also follow from this one. So to prove the previous one, you can also do it with this one. And as you see, my main message here is a unitary matrix model equal to Teplitz determinant. Why? Because sometimes it's useful to work with this. For example, in gauge theory, you work with this, and you know how to do large N and study phase transitions with the integral representation. But in statistical mechanics, there are a lot of this type of determinantal descriptions of observables. Some of them go back to work of von Sager and the 2D Ising model. And you can write them as Teplitz determinants, and you have tools which are specific to the fact that it's a determinant. For example, with a determinant, you can easily do small n cases, but you can also do with certain theorems like Sego theorem, large N behavior. So sometimes it's useful to think in terms of integral representation, namely random matrix theory, but sometimes there are specific tools which are relevant from the point of view of Teplitz matrices, because this Teplitz matrix come from Teplitz operators, so there are many actually results there. Yes, and this D are the Fourier coefficients of this sigma that you were asking, Mauricio. So this sigma, if you write it in terms of Fourier coefficients, these are the entries of the template matrix, essentially, which are the entries that I showed before. So the type of matrix integrals I'm advancing here, I'm going to need for the XX model. So basically, the XX model, the fact that I choose, the fact that I choose the XX model will fix my sigma that you were asking. And in this case, because we're in the unitary, because it's periodic boundary conditions, it will be this factor here, which this is the Gross-Witten potential. That Gross-Witten in 1980 ended studying this by studying 2D Young-Mills on a lattice, on a single plaquette. So you put the Wilson lattice action. The Wilson lattice actions give you this, basically. And they were the first that they uncovered the phase transition. Back then, it was something really a bit surprising to them. And if you look at the title of the paper, it says possible third order phase transition. So, and these are not people. So at the beginning it was, but then very quickly many people started studying phase transitions. These are toy gauge theories, if you want, because they are in 2 dimensions. But anyway, later on it has been generalized to more. And this reference has almost like 1,000 citations. But as far as I know, they always consider here, instead of IT, they consider what here would be imaginary time dynamics, so the thermal average. So imagine if you have, instead of IT, you have beta, you will have beta here, then this is exactly Gross-Witten. PBC is periodic boundary conditions, so it means that my spin chain will be a ring. And ABC, it's a special type of open boundary condition where in the origin, it's absorbing. It has an absorbing condition, like if for fermionic picture, it's easier to see. If it touches this boundary, I mean, it's 0 at the boundary. So this is just a boundary condition. Okay, yeah. So the notation PVC is standard, but the ABC is not the standard notation for this type of absorbing boundary condition. It means. Okay. Yeah, in the second case, yes. Yeah, exactly, yes. And okay, the way I've written here, this is for the case of L infinity, so the chain is also infinite. Okay, yeah, okay. So, okay, and then, like I said, a multiple domain wall can be considered, but then to deal this. And for a lot of physics, maybe the extra work that you have to do with this is not. This is, for example, if you compute this is kind of subleading, because as you see, if you put it in the potential, this goes as a logarithm. This is always a polynomial, right? Because it's not obvious, these are characters, but this is always a polynomial insertion. So it goes into the potential as a logarithmic term. So for large n limit, it's always subleading because it gives a polynomial modification of your partition function. But also, if you do the saddle point approximation, the large n limit with double scaling limit, this is totally, I mean, it doesn't contribute to the, so you can ignore it for certain problems, okay? Yeah. Yeah, the same, sorry, when I say what I tried to say at the beginning, this is, I like to blame my collaborators on this because I like the notation XX, but they like XY, but it's isotropic XY. The XY is way more general when you have different interaction for the X and the Y. But yeah, my apologies because this is and both I mean XX. Exactly, correct. Yeah, that's it. yes. Thank you. And that's important point actually because the XY to do with this is actually way harder, and it leads to a matrix model. If I have time, I'll say it at the end. That it's totally been unstudied because the dispersion relation when you fermionize of the XY after doing a Bogoliubov rotation is so. Yes. XY is not, it's interacting. Yeah, exactly. Yeah. So yeah, they seem similar, but it changes quite a bit one from the other. Yeah. The XX is always very specific, yeah, for transport properties also, etc. Yeah. Okay, so let me summarize some of the main results, which these are specific to the XX model, like I said, and to domain wall states. So these are basically one result that, well, it can be set in 3 parts of this paper, which is to uncover this dynamical phase transition, which we wanted to see. We know Gross-Witten has a phase transition. What happens when you complexify the parameter? like I said, there are almost 1,000 papers on the Gross-Witten standard, but this complexification, maybe because physically had not appeared before or was not necessary, apparently is not in the literature. And indeed, the matrix model is much harder to analyze. Normally, matrix models can be done very rigorously, but here we need to do some saddle point method and some numerics also. Okay, let me state the three results are that if we define the dynamical Loschmidt echo, as I said before, is the log of the Loschmidt echo, and we take first the L infinity limit, so means infinite chain, and then the limit n to infinity also. So I have to flip an infinite number of spins. Of course, this setting up to here, it won't go well with experimentalists if you tell them about that, because you need to tell them an infinite chain and you need to flip an infinite number of spins. So if you, I mean, this is not very realistic, but in that setting, which mathematically is the simplest, we study we find that indeed there is a third order phase transition in this free energy, dynamical free energy, which happens at this critical point. Nicely enough, we'll see that this is not the analytical continuation of the Gross-Witten phase transition. And this is something that is well known when people study Loschmidt echo. But at the beginning, people claim that you can study it as equilibrium partition function, meaning the parameter is real, and then do analytical continuation. But then many people start finding counterexamples where you cannot do naturally this analytical continuation. Our results is a confirmation of this fact, but in the setting of this double scaling limit and of this phase transition.
So
Yeah. Yes.
So it's good that you're explaining the difference with Gross-Witten, but I want to understand.
Yes.
It's still the values.
Yes.
Correct.
Yeah. Very nice point. I'll discuss a little bit when this is totally correct. And Gross-Witten, well, maybe I'll say it in a few slides, but okay, Tomoki, how I'm doing with time? I'm okay. I'm okay. Yes. I'm not so sure. I'm okay. Yeah. Okay. So it opens. Gross-Witten is known to the eigenvalues are on a circle, and you have the weak coupling phase. All the eigenvalues, the support is the whole unit circle. But then when you do the ansatz of having the full support, you realize that there is a point in the parameter that it develops a zero. This basically means that it opens a gap. Then after this, it will become negative. The density of states cannot be negative. So the phase transition in Gross-Witten is of the opening of a gap, which happens at pi or minus pi. And the second phase, the strongly coupling phase, has the support is not the whole unit circle, and it has a gap there. I mentioned this because in matrix models, like I said, it's rather useful to have third order phase transitions, but the underlying mechanism of the phase transition is very different. So this is a unitary matrix model. This is the opening of a gap, is what happens here. We will have the same. Let me maybe say it on the side. The only thing is that now we don't go in the unit circle. We have to deform it in the complex plane, but the same concept appears. Yeah. Then the other case of the absorbing boundary condition is a bit different because, okay, but I don't want to complicate the talk too much. I mean, this paper is like 60 pages, so it had to be summarized in some way. And so then, because this is the right question, and David is a real quantum information person, and he pushes, also in the past, he pushed both us hard to know what happens with finite chains and realistic conditions, because he wanted to be able to talk to his experimentalist friends and be able to try to convince them maybe to do an experiment on this. So we studied two other settings. Then we need to study the finite chain. What happens in finite chain? The matrix model, which I still haven't written, well, I brought in matrix form, is discretized. And so basically what the matrix model, if the chain is finite, namely if L is finite, becomes the Riemann sum of the original matrix model. And this makes it way harder. And in fact, this discretization can introduce additional phase transitions because now the spacing between eigenvalues has a bound. It means that the rho has a bound, and when this bound is not satisfied, it means that it triggers additional phase transitions. So we have to, and one thing we have to look is that the first phase transition that is triggered by this fact doesn't happen before ours, because then would spoil. So by doing that, we prove the second main result, which is at the end of the paper, section 7, I think. And we show that the third order phase transition persists in the thermodynamic limit, which now we take them both at the same time to infinity. But this is in condensed matter, is a rather standard setting. This is a rather standard thermodynamic limit, because both are fixed now. So if we fix L over N, and this is a small L, and this is the inverse of a finite density, because N is the number of spins that I flip, right? In the fermion picture is the number of fermions I have. So this describes a setting where I have a finite density in the thermodynamic limit, because the quotient of these two quantities is fixed. And we shown that in order that this phenomena that I was telling doesn't spoil the phase transition, we need that at least the size of the spin chain has to be 20% bigger than the number of spins that I flip. Okay, this is what we found. But this is already a setting which is better to describe to experimentalists, because this is like a thermodynamic limit, but in a finite density ratio. Before, but here we take them both at the same time, keeping the density of spins flipped constant with respect to the size of the chain. All right, and then the third problem also needs to deal with these discrete random matrix ensembles, but these are discrete unitary random matrix ensembles, which by the way appear in gauge theory also, because Minguala had papers on Chen-Simon's matter with vector matter, and he had, I say this because it's a gauge theory audience in part. This type of discretization of unitary matrix models have appeared in the high energy physics literature. So basically the result for a finite chain is, at least for the weak coupling phase, we can prove, this is always to David, that to see that with a finite chain, the results that we obtain for the infinite case, for the continuum model, are the error that how it changes the discretization, the result that we have, to prove that it only introduces exponentially small errors. So we find that the difference with the thermodynamic, with this result that we find, is exponentially small in the difference between the size of the chain and the number of spins that I flip, if the size of the chain is at least twice the number of spins that I flip. So in this setting, for a finite chain, and to be able to see that having this discretization doesn't change much the result, or at least only exponentially small corrections, I need to flip at least less than the half of the spins of the chain. This is the maximum I can flip. And this is what will create a limit, and this is what, depending on this condition and how good it is, it makes a difference if experimentally you can measure it or not. You see, this is mathematically it goes sometimes very often when you do numerical analysis of integrals, you don't know how to do the integral, you do the Riemann sum, right? In this case, it's kind of opposite. We want to see how well the Riemann sum is approximated by the integral. So this is what happens in this third point here. And what we find is that this condition is satisfied. The difference is exponentially small. Okay. Now, I was good on time, but I think now. Okay. So, yeah, you're doing on purpose now. Yes. Yeah. Oh, 2 previous slides. This is very tricky, because you're my neighbor at CIMIS, and then yes, this one. Okay. Yeah, boundary conditions. Yeah. Yeah. Right. We have some small t expansion for the logarithmic echo, and there is a certain universality there. It only depends on traces on. I haven't checked. I don't remember if then it's we see the universality regardless of the gauge group. I will need to check it. But yeah, maybe that's correct. Yeah. But I don't want to talk too much about ABC, because then it will be. I mean, the talk is going to be very complicated. So, yes. Yeah. Yeah. Different, but one thing I'm going to show is that in this plan, and I will have some plots on this, I'm going to show this explicitly what is the difference between the free energy. One is twice the other, basically. So in this double scaling limit, I think I'm going to find that if I remember correctly, I have the plots now. Free energy is basically the same in the planar limit. I don't know about more delicate, but yeah. Okay, I'll try to say more about this as it goes on, but yes, I'm concerned about that. So. Okay, so no, but definitely we can discuss more about this. But maybe with the plots, I think we will maybe answer. So I want to say, for the people who are maybe familiar with this, these are different in several ways. First of all, it comes from the matrix model, so it's of third order, right? So the phase transition is of third order, which is exotic. And if you talk to a condensed matter person, this is a very exotic thing, and I don't think experimentally has ever been measured. But the random matrix people consider it rather universal. It's true that this is because of Gross-Witten and Douglas-Kazakov phase transitions, but which appear a lot in many different contexts. But in random matrix theory is rather useful, but normally it's the same models that have this third order transition. What is this is dynamical phase quantum transition. Okay, I think maybe I flipped I permute the letters at some point, but yes. So this is the type of phase transition we are studying. This, okay. This is a shortening for, okay. So yeah, RMT is random matrix theory. Yeah, yes, thank you. It's important to clarify because yes. So we use the standard random matrix theory, and which is very customary in quantum field theory. Basically, this is why I'm a bit different. But let me go to the model itself because this may be slightly more concrete. So this is the matrix model. So this is Gross-Witten, and Wadia, Gross-Witten-Wadia matrix model from 1980. The difference, just this imaginary part here. But this complexifies the weight, and this creates a lot of problem. Remember I told you, any unitary matrix model, you can see it as a template determinant. And in StatMech, it's more useful perhaps to look from the determinant point of view. The standard Gross-Witten-Wadia model is a determinant of Bessel functions, but the modified Bessel functions. Now we have here the J's, which are oscillatory. The others are monotone. So this is a matter. Basically, so what I need to study is this determinant. But this determinant is not solvable at finite n. It has no solvable. So there are matrix models which have a seemingly much more complicated weight function. But however, for example, you can have a theta function here, and then it describes Chen-Simon's theory. A theta function here would seem much more intimidating, but it happens that the Bessel become Gaussians. And then this determinant is computed. Exactly, and this would give you the free energy of UN Chen-Simons on S3. You know very well this, Professor Romo. And but now, that model is seemingly simpler and studied for much longer, but there is no known explicit expression for this object or this. Even in the Gross-Witten case, this is my point. So the standard method in random matrix theory, I don't want maybe to give too many details, is to study the saddle point approximation in a large n double scaling limit. So we write everything, we put also the van der Monde part. This is the other way back to write the hard measure. I mean, when it's unitary, so you have these phases, but this is totally equivalent. And this is what changes for symplectic, and it becomes different, but not with beta. So now we can study the saddle point method and to try to extremize the action written before. And this is totally the standard method. Like I said, it's more than 3 years old in a sense. But the difference here is that we have this I tau instead of beta. And this makes problems. Why? Because basically, this integral is expected in the large n limit to be dominated by saddle points of the action. But now we have to pick up the saddles are not on the unit circle anymore. And we have to go to the complex plane to pick them up and extremize properly the action. And obtain, this is the standard result of the saddle point method, that the large n limit of the free energy is the real part of the action evaluated in the saddle points. So this is the technical part of the paper, which I wouldn't say is fully rigorous, at least at the mathematical level of rigor, because we have to deform the contours, but we deform homotopically the unit circle. And we find a connection with other methods in mathematics. So, okay, I'm okay. So basically, this is what also Leo was asking, that is the mechanism the same? You have a density of states. Yes, the thing is that the Gross-Witten opens a gap on, so the Gross-Witten, the eigenvalues distribute on a circle here, and you can work with, like I said, an ansatz that the rho is the whole unit circle. But then if you do that, you find the value of the parameter gamma, this is the rescale beta, where it develops a zero. And if you increase it, it becomes negative. The density of states cannot be negative. So this tells you that the ansatz that this is S1 is not correct. So you need another solution. So this means that you need a second, there is another solution that has a gap here where you have no eigenvalues, and the eigenvalues distribute here. So the support is contained on S1. So this is the opening of a gap, which is one of the mechanisms of phase transition in matrix models. Like I said, there are others, like one-cut solutions, high edge, soft edge, etc. Doesn't matter. This is why also it changes a lot if a matrix model is, 5 minutes. If a matrix model is Hermitian or unitary, because the mechanism of phase transition can be very different. Now, the same thing happens here, but in order to compute the solution of the saddle point equation, we had to deform this contour. But this opening of a gap mechanism is still the same. So we have an ansatz based on the solution for the standard Gauss-Witten model, and this has complex zeros on the complex plane, this density of states. So we have a row that now satisfies the saddle points equation with a contour deformed. And we need to see when the smallest zero of the density of states hits the contour in the complex plane. So it opens a gap, but it opens it in the complex plane, but always in a homotopic, well-controlled formation of S1, that in a tau to 0 limit, it becomes the unit circle. Okay, so I have short time. Let me tell you, this is maybe the main results, and there is even it looks very innocent, there's quite a bit of information here. So by doing this method, deforming the unit circle, which is the tricky part, like I said, computationally, we obtain for a small tau critical, when this tau critical is when this zero hits the contour, this first zero hits the contour, this is T squared. This is exactly as Gauss-Witten. And this is what the behavior of the free energy, and Sego theorem tells you that, the Largen limit of the Teplin determinant, if there was no phase transition. If there was no phase transition, this matrix integral that I brought, or this determinant, it's known to be in the Largen limit without scaling, a Gaussian. So remember, this is the log, so quadratic. But by extending the saddle point equation, we find this property for the second order derivative is as we expected. Normally, we have to approach this problem from this region because it's simpler to analyze. And crucially, what we find is this, that approaching to for the critical side from the left, the third derivative is not 0, and it should be 0 if this was going to continue, right? So this signals a third order phase transition automatically. And then, so this is the signaling of the third order phase transition, because otherwise this would be 0, because then everything has to be T squared. And therefore, we also obtain for large tau that it behaves like log of tau. So we know it's not like the standard Gauss-Witten, because Gauss-Witten has this log term and it has a polynomial in tau also. So this tells us third order, and this tells us that this third order is different from Gauss-Witten. Okay, and I have to accelerate, I think. Yeah, these are some plottings here. Like I said, this is the discrepancy from tau squared. And yeah, and then we did a section on experimental accessibility of the phase transition, which was written by the mathematician in the collaboration. But apparently, the mathematician there knows more experimental physics than the physicist in that case. So we crunched some numbers, and basically, I think I'm running short of time because we studied for finite, the difference between a finite chain, for example, for 9 qubits, for 9 spins, and we flipped N3. The error we find from the expected curve, if there was no phase transition, is a 4.5%. So this, in principle, should be measurable. Okay, I have another comment here on this. That so this is the most optimal we could get. That if the speed chain is 9 spins, the time evolution is short, and the total deviation to be detected at the -3 level. So that in principle, experimentally, has to be. So this is how it differs from, you see, from tau squared, and you see from L11 and L infinity is basically here with this resolution here in this, we see no difference. This is with 4 spins flip. So we push hard in order to have the best numbers possible, and we're told by this group of people that it's on the boundary of what experimentally I think possibly can be measured. Like I said, I want to emphasize, and I think I'll skip the open problems. I want to emphasize that the Gauss-Witten, and this is the standard Gauss-Witten, and this is ours. So there is a bigger, as time goes farther, I mean, there is a bigger difference because here it had a linear term and we only have a logarithmic term. So it's significantly different from, so you cannot continue real-time dynamics from imaginary time dynamics in a naive way because the two phase transitions are different. Yes, it starts to breach off exactly at the same critical point where the phase transition is, because in the weak coupling, everything is the same. But then is the strongly coupling phase that changes. And so at this critical point is when it starts, because the Gauss-Witten has tau, if it's not tau, it's beta there, right? But in logarithm, and we only have a logarithm. So right at the critical point of the third. Otherwise, it's a mild phase transition because it's a discontinuity on the third derivative, and we study also that. So then let me just finish, I think, because I'm out of time, just by saying that you can work with the matrix models in the same manner if you work with fermionic systems. So if you this is okay, there are a lot of things that could be said here, and this is what is in the appendix of this Hawking Page paper, because the fermionic model and the spin models are known to be mapped one to the other by Jordan-Wigner transformation only with nearest neighbor interactions. But if you have more than one nearest neighbor interaction, which I didn't add, you need to have more cosines you have to need more potential. They are not the same. The models are different. So Jordan-Wigner is good for nearest neighbor. So what I'm trying to say is that you can find a matrix model description of the same type, but with fermionic models. But these fermionic models are in principle different. We studied in why there is equivalence of the Loschmidt-Echo amplitudes. It depends on this is a very specific type of state that we work with. And okay, it can be explained with more detail. I could give more details, but basically the main result is this, that for a fermionic model of this type, you don't need only to have the dispersion relation, a cosine of k, which would be the xx. So for example, the xy that you were asking me, after Bogoliubov rotation, is diagonalized and it has a square root, or Kitaev chain, for example. So you would need to study this square root dispersion relation as your potential here in the matrix model. And this is completely open. No, there are no matrix models studied with this square root. So this is a kind of open problem. You can study many more fermionic models with this formalism. And of course, the phase transition so on, one needs to see what happens. So let me just conclude. I mean, I have open problems, but I'll skip. I wanted to say this is more formal, and I want to tell Mauricio and Babak and maybe more people about this other connection, Tomoki, this connection, but we'll do it in some other occasion. I want to, also the last slide is very important because it's something I learned at BIMSA. So yeah, I think I'll finish here, and if anybody's interested on the open problems, I'll be glad to talk. So thank you.
Question?
I think I had 2 minutes.
What is dynamical free energy?
Yeah, dynamical free energy is basically the log of this Loschmidt-Echo, but this Loschmidt-Echo has IT, so it's real-time dynamics. So this is why they call it dynamics. People in the studying Loschmidt-Echo now study it even with complex time, and then they like to study it on the complex plane and see the pattern of zeros and poles. They give you information. Yes, for example, the first zero tells you about what is called the quantum speed limit. Which, yes.
You consider the imaginary time. I mean, e2 minus t times.
No, imaginary time dynamics would be the thermal state. So let me just. So basically, what I did in this PRX in 2014 was to study this object. So this is what I call. You can call it certain thermal average, or you can call it imaginary time dynamics, because this is beta. Beta is real here. But now for Loschmidt-Echo, this is what is the dynamical setting. In this notation, we also use the standard in the literature. So that's the matrix model part is kind of maybe what is unusual, but this is what. So this is real-time dynamics because I have the unitary evolution operator acting on the state. So basically, I see how, for example, what is it's a scalar product, right? I make it evolve on time. And then I take the scalar product and say you can, for example, study the probability that it returns to the same state, things like that. So this is what is the dynamical setting, but just because this is real-time dynamics. So the dynamical free energy is the log of this, which is the log of basically of this to the square, basically. So, and this is, if you look at this review by Marcus Heil and many other people, this is what they discuss. And if you want to do it more generally, because one of the properties is that you cannot compute with this and analytically go to this one, and this is one example in our case. So some people study now this with a complex parameter here, complex time, and to study it on the complex plane, the vertical axis gives you real-time dynamics, the imaginary axis give you, and you can see the pattern of zeros here, and it's, yeah, so sometimes people study this complex version. Which is something that I believe this kind of connection formulas I was mentioning maybe gives you an example, because you can, like I said, you can relate this to Pine level 5, and there are connection formulas there, and I think connection formulas basically relates the tau function of Pine level 5, vertical axis and real axis, and this is exactly would be passing from one to the other. If this would trivially related, the connection formula would be trivial, for example.
I mean, you take this dynamical free energy,
yes,
and you go to the T infinity limit. Or
no, no, really. What we find is that with a rescale T, we find a T critical where it develops a phase transition, which in this case is just that the third derivative of this free energy is discontinuous. So it's a very mild thing actually, because it's just a discontinuity on the third derivative of the.
Scale something.
Yeah, I rescale the time with n. Yes. And also this has like a factor here, like this is multiplied by one factor. Yes, actually, if you look at the literature, this type of quench is not the most general you can consider, or chain is such, or setting is such that L of t, this logarithmic echo, is finite for all t. Look at the Heil review for this LT behaves for if you, what I'm saying is that you make the chain infinite, the logarithmic echo, how we have defined it, and with the Australian quench setting, it keeps always finite, and in the plots, I mean, you can always plot it, there's nothing diverging there. Whereas this LT in general, in this review, for example, behaves something like this, like explicitly with L, and then it's a function f of t. So this is kind of a smaller logarithmic echo that we have. Yeah.
Another question. In the abstract, you mentioned Pine level 5.
Right. No, I didn't, because it's a good point. And so it's in the last slide. Okay, sorry, this is I even had more. So yeah, Pine level 5 is as follows. For the ABC boundary conditions, we need to have integration over the symplectic group. Basically, this means that the van der Monde now is of this form. Then this is the sign, the standard. So basically, in this model, normally the integration on the symplectic, on this ABC boundary conditions would be harder. In matrix models, unitary should be the simplest. But in this case, this type of interaction between the eigenvalues is such that you can do simple mapping, which is not one-to-one, but you can map the unit circle on the real line, and then you map this model, because this van der Monde is more complicated, but it maps in such a way. And this proves one thing, that this was a Teplitz plus Hankel determinant. Now it's a Hankel determinant, because this is a Hermitian matrix model on the from -1 with the exotic thing, which is the weight here. And this is again exotic because this is complex. I mean, this is imaginary. So this is not a classical weight. Otherwise, this would be like it would be like a Chebyshev. This could be solved with Chebyshev polynomials. But one thing that is known about this model, and a simplified version of this model appears a lot now recently in number theory, is that this is the tau function, this the integral, this determinant, Hankel determinant, is the tau function of Pine level 5. So you can relate this object with the sigma function of Pine level 5, I think in the Okamoto formulation of this. And there are a lot of results for this Pine level 5. The first ones go back to Jimbo, too, but more recently by Elisovin, collaborators and others, you have irregular conformal block expansions in C=1, I think, conformal blocks, and connection formulas. So either this or study the zeros of the tau function, which now people like Bertola have studied this problem, but it's very analytically, this is very hard. This can be useful to extract physics from knowledge of this tau function of Pine level 5. Yes, but yeah, okay, that's one open direction. So basically, but this connection only holds for the absorbing boundary conditions. Possibly the other periodic boundary conditions with a different argument is time level 3. But and this is known in a book by Forrester. You can in random matrices. You can see this connection. This would be a more formal development, but it would be nice if this connection formulas, it seems something very theoretical in this business, basically tells you something physical, that you cannot go from the imaginary time and real-time dynamics in a trivial manner. Okay, so yes, this is the connection with.
Any other questions?
Yeah. Okay.
Free energy.
Yeah.
So what's the difference between the dynamical and the thermal free energy? Because according to this, it seems
Yeah.
that it's only
Yeah.
a weak mutation. Why we
Yeah.
need the dynamical?
Well, experimentally, apparently, and I'm not an expert on that from what I've been told, I mean, it's a huge difference because in one, you just need to do real-time evolution. You let the system run. Apparently, this is way simpler to do. The other, you have to stabilize the system in a thermal state. This is much harder to do. If you talk to people closer to the physics, I believe they'll tell you that the real-time dynamics is more interesting, experimentally and in general. So physically, that's the difference. It's very different, actually. Mathematically, the only difference is that my unitary evolution operator, in one case, is the standard one, and in the other, it has this imaginary time. Beta is imaginary time, if you want. So the mathematical difference is what you can see in part. In our paper, we show one way in which these are not naively related. So this part of what you learn from doing this, basically.
So now for the phase transition, it's just some other parameter is just from temperature change to real time.
Exactly. Yeah.
But does this cause some problem? Because when you maybe examine some free energy function in some complex plane after this weak mutation, because we know some Yang-Lee singularity.
Yeah.
Real axis. After you is this complex?
This is what some people in this area they do. That is what I was mentioning also, that they study maybe in a complex time and then they look at the complex plane. Depend the pattern of zeros and poles you have there. You have these difficulties that we are talking about. Yeah. So this is a non-trivial. And at the beginning, people thought that you could go from one to the other, but then very soon people gave counter examples explicitly. Like, yeah.
Thank you.
Yeah. You're welcome.
Any other question? If there are no questions, then let's thank the speaker again.
Sure. Yeah.